Okay, so my talk today is on a hazard and risk model for induced seismicity in the Groningen gas field with an emphasis on modeling site amplification. This is an ongoing project. The project has been going on for over 6 years, but what I'm presenting today is not the latest version of the model. What I'm presenting today is a mature version of the model that was published on a paper a couple of years ago. The project is ongoing because of further refinements that are being made to both the hazard and the risk component of the model. But the essence, the core of the model is what's published on a paper. In fact, I have here a paper, a regional site response model for the Groningen gas field, and it was published in 2017. I have to acknowledge the team, the full team that developed this model. The lead of our group is Professor Julian Bomer from Imperial College. The group includes Peter Stafford, also from Imperial College, Ben Edwards, who is in Liverpool and who is a seismologist. He's the seismologist in the group, and Pauline Kruger, who is in Deltares, which is a research organization in the Netherlands. Funding comes from the owners of the gas field, which is NAM, and I have had various students that helped me in the project throughout. I probably should have included all of them. I include Maddie because Maddie is the one that has been recently helping me work on this project, and some elements of the work I'm going to highlight here. So the outline of my presentation, I will introduce background to the project, talk about the model framework, and then emphasize the component related to the site response analysis, which is where I have contributed the most of the work. Okay, if we have time, I will talk about some possible future work or the current work that we are doing in refining the model. So starting with the background, the Groningen gas field is located in the north of the Netherlands. I assume you're good in geography, so I didn't indicate where the Netherlands is, but it's in the north. It's close to the North Sea, in the northern side of Europe. So you have here Belgium, Germany, Netherlands is to the north, and Groningen is in the northern tip of the Netherlands. This information is from 2017, so it may have been updated, but at that time, it was the 7th largest gas field in the world based on initial reserve. However, some 70% of the gas had already been produced, and still, based on the current reserves in 2017, it was still the 13th largest gas field in the world. It was discovered in 1959, it was taken in production in 1963, and this gas field is in a rural region of the Netherlands that has some interesting history. Part of the history of the Groningen region is related to the use of peat as a fuel. And what makes that interesting is, for those geotechs, or for those of you that are geotechs, you know that peat is a highly organic material. It's so organic, I mean, it's soil that you use it as fuel. But it has a behavior that is not typical of other soils, because the structure of peat includes many roots, many organic material, which means that its behavior tends to be different from that of non-organic soils or inorganic soils. The gas contains 14% nitrogen and has lower calorific content than other fields. And you may ask, why am I mentioning this? But it will come back to, in non-technical aspects of this work, I will come back to talk about this later on. The owners are Shell and ExxonMobil, that is operated by an organization called NAM. And the importance of this field for, not just for these companies that own the gas field, but for the Dutch government is difficult to understand, because some of 93% of the gross revenue is paying in taxes to the Dutch state, and the taxes from the gas that's produced here constitute a large part of the tax income of the Netherlands. So the extraction of gas has led to the occurrence of earthquakes. Okay? And these earthquakes are well recorded by a local network. In 2012, in 2017, when this model that I'm presenting was developed, the largest earthquake up to that point was the 3.6 Huizinga earthquake. Since in 2019, we have had one earthquake that was larger, a magnitude 3.8 earthquake. You can see here the data, the database in terms of magnitude distance. This is again 2017 data. This is much richer today with a magnitude 3.8 earthquake that will cover a large range of distances here, and with a significantly larger amount of earthquake at larger distances, because the network has both grown, and as earthquakes have kept occurring, so the density of recordings is larger. Okay. This is the network that is used to record the earthquakes. There are two types of stations, B stations and G stations. The B stations are accelerographs that are placed at the surface, and they have been there for a long time, so they recorded a lot of the initial earthquakes, or the first earthquakes that occur after when earthquakes started occurring in the 2000s. And then the G network is a network of downhole, of borehole arrays. So there is a geophone at the surface, and there are 3 additional geophones at depth intervals of 50 meters down to a depth of 200 meters. So right now, a full risk model is under development. And as part of the risk model, you need to have computations of the hazard. Risk is related to damage to the infrastructure. Hazard is related to the intensity of the ground shaking that results from the earthquakes. And the earthquakes that produce this shaking are well understood. So this is a sketch, a schematic of the gas field. And you have here the Slochteren sandstone, and this sandstone layer is where the gas is located. So what happens? As gas is extracted, the sandstone layer shrinks. It's a consolidation process, essentially. As you're extracting the fluid, the layer is shrinking. And the shrinking, normally it would lead to just uniform deformation across the field. But what happens is that this sandstone has a lot of pre-existing faults. And these pre-existing faults create planes of weaknesses, and the deformation of the shortening of this layer gets concentrated in episodic slip events that occur in these pre-existing faults. Each one of these events is an earthquake. So this is interesting because it means that you can predict the amount of elastic energy that's being generated because of the gas extraction. That energy is simply the amount of shrinking that's occurring, the volumetric shrinking multiplied times the modulus of the sandstone. So you can predict the amount of energy that needs to be dissipated through the earthquake. So the seismicity is well understood. A kink to this, however, is the small probability that is considered that one of these events triggers a tectonic event. A tectonic event being now an event that's releasing pre-existing stored stresses in the crust. Okay. But I'm not going to talk more about the seismicity per se. If you look at the different components of the study, you start from the gas production, which based on the production, you can develop a model for rock deformation. And based on the analysis I just described, you can generate a model of seismicity. The seismicity generates ground shaking. Okay? And the ground shaking is coupled then with a model for the exposure of the infrastructure at the region and the fragility of that infrastructure to predict the amount of injury and the damages to the infrastructure. I didn't prepare this figure, this Julian Bomer prepared, but I like it because I can emphasize the fact that the keystone in this bridge is the ground motion. The ground motion model is essentially the link between the seismological model and the fragility and risk calculations to estimate the impact of the earthquake on the built environment. And that's what I'm going to focus on. I'm going to focus on the ground motion model framework. Okay. By the way, if there are questions as I move along, I welcome the questions. They are always nice because it makes me believe at least that you are paying attention. So, okay. So what's the framework of the ground motion model? I put just a sketch at the left of the Groningen gas field. Okay. And this Groningen gas field has, this is a shear wave velocity, matched more or less to the gas field. And you see that in the top part are all our sedimentary deposits. They have relatively lower shear wave velocities in the order of about 500 meters per second to 600 meters per second, with very low shear wave velocities near the surface. And at this point, you go into a lower Cretaceous unit, and there is a big jump in shear wave velocities. Okay. This is the upper North Sea group. So this is, we call it the North Sea group boundary, or NSB for short. And our model of site response focuses on the effects of these North Sea, the upper deposits on ground shaking. So how do we model this? We start with ground motion recordings at the surface. This is our data. This is the data we have. This magnitude and distance, this plot I showed before of magnitude and distance are a plot of magnitude and distance of recordings that we have at the site. We use a linear model to convert the surface motions to what we expect at the NSB boundary. Okay. And these records now that have been stripped of the impact of the site response model are used to constrain a seismological model. So the seismological model then is representing the ground motions at the NSB boundary. There is representing the recorded ground motions at the NSB boundary. Okay, so if we couple now this seismological model with our site response model that models the transfer functions, then we can reproduce the ground motion recordings. That's great, but our interest is not to reproduce existing ground motions, but to predict future ground motions. So we use this seismological model, and we use it to generate a ground motion prediction equation that will predict ground motions at the NSB boundary for future earthquakes. And this exercise is not simply an exercise of, okay, let me just try to reproduce the data I have, because the data exists in a magnitude in a limited magnitude distance space. But what I want to predict for future ground motions includes larger magnitudes and a denser predictions that need to be worked at the range of distances as well. And those predictions have to be now coupled with the model of site amplification, of amplification functions. But this site amplification model, which is in terms of amplification functions, has to also work in the nonlinear range, because the soils are expected to go into the nonlinear range. The recordings are small enough that are small enough in intensity, we can assume they behave linearly, not so for the amplifications. Okay? So the reference horizon is this base of the upper North Sea group, and we chose this as a reference because it's a strong impedance contrast. It's present in the entire field, meaning that we can assume that the ground motions that occur at this level, or predicted for this level, are uniform across the entire field. It's about 1,400 meters per second. What we want to do with the site response analysis is two things. One is a linear model in terms of transfer functions that are predictions of site effects in the Fourier domain, or amplification factors, which are the equivalent ones in the response spectral domain, so that we can take the recordings at the surface and deconvolve them to motions at the NSB boundary. But then in forward analysis, we want to be able to take the predictions now at the NSB boundary from the seismological model all the way to the surface. And in this case, the amplification factor must capture both linear and nonlinear side response. Okay. They also have to capture scenario dependence on linear side response. I will talk more about this later. And they have to capture, see, the key here is that these models, the amplification, what it allows us is to take motions that we assume them to be relatively uniform at the NSB boundary. And now we need to, we are able to capture with our amplification model the spatial variability of ground motion. But because we are applying this within a probabilistic framework, we also need to be able to capture all the uncertainty that's implicit in the parametric, both the parametric uncertainty, model error, and motion-to-motion variability. Okay. Now the question is, how do we capture side response? How can we capture this? And we really have a range of options. We could do it in a fully empirical manner, meaning that we can use the instrumental data that we have to compute amplification functions. However, that creates problems. First, we only can apply these empirical functions to where we have instruments. We will need some way of interpolating in between the instruments. Second, the recordings allow us only to capture linear side response, but we know we have nonlinear effects as well. Okay, so that's a problem. And then we are only measuring the ground motions to magnitudes up to 3.8. Okay? But we need predictions of side response for ground motions that are much larger, because our model predicts magnitudes up to magnitude 5 or so. So we are limited in the use of empirical models. So in this case, it doesn't work. So we need an alternative. An alternative is to use proxies for side response. And this is what's done by the ground motion prediction equations that we normally use in hazard analysis. And these proxies for side response are simplified measures of the side, or simply parameters that represent the side. For example, the average shear wave velocity over the upper 30 meters, or the side period, etc. And there are advantages to this. They can be calibrated with empirical data and with numerical analysis. So we can make use of the empirical data, and we can also use numerical analysis to calibrate this. We understand these parameters well because we have been using them in ground motion prediction equations for a while already, for over 20 years. They have advantages because they are there is a simplicity in just simply using proxies parameters to capture side response. Because we have used them so much, we know more or less the type of behavior that we expect. Okay? However, there is a disadvantage. And here I showed in the right one such model. So what's the amplification as a function of VS30 for different intensities of input motion? This is from the work of Norm Abrahamson and Ronnie Kamai. However, the disadvantage is that it is a very simple parameterization. And as a result, you can have cases such as this one. This is from Julian Bomber, one of Julian Bomber's publications. Two sites that have a very different profile, yet they have the same VS30, or almost the same VS30. But VS30 is a simple parameter, side response is complex. And when you look at these profiles, you would expect that they would behave differently. And in fact, they do. The site amplification that you predict for these two sites are very different, both in where is the period for highest amplification, and also in what the amplitude of the amplification. Okay. So this is a valid approach, but it implies a simplification. Another alternative is to go and use all the analytical tools that we have at our disposal. So perform side response analysis using full VS characterization. And that has the advantage that we don't have to revert to a simplified parameterization. We can use all the information that we get from side response analysis. However, in order to do that, we need to characterize the full VS profile, not just at one side, for entire field, because we need to do predictions in the entire field, and we need dynamic soil properties for all the soils in the field. So we need a lot of things to do this. But in this particular case, we have that information. The Groningen field is well characterized. There are multiple VS measurements at the ground motion stations, and the ground motion stations are well distributed across the field. These measurements include measurements using different approaches: surface wave characterization, cross-hole, downhole. Yeah. And there has been a tremendous amount of work that has been done by geotechnical engineers in the Netherlands to develop a geostatistical model of practically the entire country, but in particular of the Groningen region. And this geostatistical model is a model that models a grid of 100 meters by 100 meters. On a grid of 100 meters, models the profile down to depths of about 30 meters. So in this model, it's called the geotop model, we can query the model and get information on what soil types we have at different depths in the entire field. And one of the beauties of this project has been that when we use this geotop model, where we take soil units, develop a correlation between index properties and shear wave velocities, and thus develop shear wave velocity profiles, and those are measured in red, those are shown in red here, and compare them with shear wave velocity measurements that were obtained later, the comparison is amazing. So we can trust the shear wave velocity profiles that are inferred from this geostatistical model. Okay? In addition, we are using also information from all the geophysical experimentation or geophysical characterization of the site that was done for the gas extraction. So we are okay. We have a lot of data. We can characterize the velocity across the field. And for that reason, this more sophisticated analysis is possible at this site. Okay? So for the different elements, when we are doing predictions at the recording stations, we have, for the most part, especially now in this iteration of the project, measure the velocity profiles. When we are doing forward analysis and are extrapolating our analysis, or we are trying to predict across the whole field, we use the predictions from our geostatistical model. And also, the predictions are not blind, because we have, at least on the recording stations, we have recordings that can help us constrain the uncertainties in our model. Okay. And one very important thing to emphasize here is that what we are trying to do with our site response analysis here is essentially to capture the differences in amplification functions across the field. And this is because we are using the same types of analysis to go from recordings to NSV that we are using from the NSV to the surface. So the absolute value of our amplifications are in a way self-correcting. What matters is captures difference between different locations. So in a way, you can think of our amplification, our site response model, as a tool to interpolate between recording stations to capture the impact of site response on predicted ground motions. Okay. So for site response analysis, there are many questions that we need to answer. One question is choice of method. Which method do we use? How do we generate input motions? How do we generate the soil profiles and choose the dynamic soil properties for our soils? And how do we quantify uncertainties of the modeler? So let's go through each one of these separately. For the analysis, we have, in essence, two choices to make. Do we work on the frequency domain or we work in time domain? And these are choices that anytime you're going to make site response analysis, these are choices that you have to make. If you work in the frequency domain, you can use programs such as Shake or Strata. If you're working in the time domain, you have various codes, but Deep Soil is one code that's easily available. In the time domain, you require a time series input, and you have to be very careful with how your numerical solution proceeds, especially when you have very deep profiles, because the numerical solution can introduce numerical damping. There are tools to minimize this, but you have to be careful and you have to understand what you're doing. The frequency domain you need to characterize the input motion simply in terms of Fourier amplitude spectra, and that's easier. They're also faster, and you have better control of the effects on damping on high frequencies, which is important. We lose some of that control because of the potential impact of numerical damping. And another advantage is it can be used with random vibration theory, and I will mention this in a second. So we chose to work with frequency domain. Okay. Another choice to make is, do you work with equivalent linear or do you work with nonlinear? Nonlinear analysis is a full representation of stress-strain curves, and you need to do time series analysis in that case, which we know is disadvantageous because of what we mentioned before. Whereas an equivalent linear model, you deal with a representation of nonlinearity of soils that's actually easier to get. And also, great advantage is because equivalent linear, you can work on the frequency domain, you don't require time series, as it's generally conservative. And actually, since in this case, we did want to err on the conservative side, we ended up choosing for equivalent linear. Here you have a comparison that was done by Kim et al. Of spectral of linear, equivalent linear versus nonlinear. If you work in the Fourier domain for high frequencies, your predictions used in equivalent linear can be, you can have lower predictions because of overdamping. However, these high frequencies usually don't have as much of an impact on the response spectra. So in general, when you look at response spectra, you tend to be conservative. We did this comparison also for ground motions, for particular analysis in the field, and I'm not going to spend much time on this slide, but the conclusion is the same. In general, equivalent linear was conservative with respect to nonlinear for our application. Okay? So for that reason, we chose to work with equivalent linear analysis. So our choice of site response, an additional choice is whether we use random vibration or we use time series. Random vibration theory is an approach. Let me back up. When you're doing equivalent linear analysis, you need to infer what is the maximum strain in a profile. And the way we normally do this in traditional equivalent linear analysis is you predict what is your time series of strain, you pick the maximum strain, and then from this maximum strain, you pick an effective level of strain from which you compute your equivalent linear properties. Alternatively, instead of predicting the full time series representation, you can use random vibration theory. And the advantage of random vibration theory is that it uses a statistical approach, essentially, or a probabilistic approach is the more proper term, to predict that given this is the Fourier amplitude of your strain, this is going to be your maximum strain. Okay? And the beauty of that is that if you do that, you never need to represent your input motions in time histories. You can simply represent them in Fourier amplitude spectra, and it's much easier to predict amplitude spectra than it is to predict time series. This is to show that in general, equivalently, the RVT approach is conservative with respect to time series, and at the end, we ended up picking the RVT approach. So at the end, we have an equivalent linear RVT-based site response analysis. Fortunately, there is a code that was written by Albert Kottke and Ellen Raggi when Albert was a PhD student of Professor Raggi in the University of Texas at Austin. So we use this code Strata. And that's it. That's our choice of model. The next is our input motions. In this case, input motions is not a big deal because we have a seismological model for the site. So we simply use this seismological model to generate a set of input motions or a large set of input motions. Next, soil profile. And I already mentioned our geotop model, which is a geostatistical model that tells us for any location in the field, which soils we encounter in the field. However, we don't just need what type of soils we have. We need relationship for shear wave velocities with the soil types. And in order to do this, we looked at a large body of shear wave velocity data across the field and developed unit-specific models that predict shear wave velocity for these different units as a function of confining stress. So which means that for each of the units that we have, we can access these models and predict both mean and uncertainty of shear wave velocity profile for each unit and values that are changing with depth as we expect for because of confining stress dependent of shear wave velocity. Our small strain damping, this is the model component that changed the most from the iteration of the model that I'm presenting here to the current model. So conceptually, though, it's still the same. We have laboratory estimates of small strain damping that come not from testing soils from Groningen, but from applying existing models of small strain damping that are keyed to index parameters of the soil, plasticity index if we have dealing with clays, or CPT, tip resistance if we are dealing with sand, or relative density in reality. So we have models of what's our small strain damping based on correlations that were developed using laboratory testing. However, we also have estimates of the equivalent damping using the borehole arrays that we have in the field. And how do we make these two compatible? Well, we scale our estimate based on the laboratory. We scale them so that we have an effective damping that's compatible with the attenuation that we observe in the borehole arrays. Okay, so that's how we built our damping model. And I'm going to repeat this because I know I said it before, but it's amazing how well of a match we got between the estimated and the measured VS profiles. This is at the B stations where we initially had measurements. This is at the G stations where we didn't have measurements at this time. We do have now, but if you take the travel time that you infer from the borehole recordings, it compares very well with the travel time that you infer from the velocity, from the estimated velocity profile. So we have an amazing match of estimated and measured VS profiles. And I have to mention this because I think it's really cool. For intermediate depths, for field characterization, for exploration purposes, they use a lot of geophysical refraction methods where they use explosives and you measure the time that the waves, seismic waves, go down to the base, to the bottom of an impedance boundary and come back to the surface. When you do that, those explosions generate a lot of surface waves as well. Okay? This is called, geophysics is called a ground roll. And when you're doing refraction, these surface waves are noise. So this noise is eliminated. And some of these geophysicists had stored all this noise somewhere. These experiments were done in the 80s. And they had a brilliant idea of, well, this noise is really for us a really large surface wave experiment. So they went back to this noise and they used it to make inferences of what the velocity is in the intermediate depth layers. For geophysical exploration, those layers are useless. For us, they are key because it gives us a model in intermediate depth. And for large depth, they had a few boreholes across the site, deep boreholes that were measured using sonic probes. So we have direct measurements of velocity at depth. Okay. The near surface profiles have, on all the velocity profiles, we have uncertainties because, and we use a randomization of velocities to capture these uncertainties. So this is, we use the Toro model, which was pretty much the standard model to use and still is for randomization. And that's it. Those are all our elements for the side response. But again, side response is not the end product here, or not even the ground motion model is the end product. Our end product are fragility curves. So this work is not my work. This is work that was done by the team. I presented because I know there would be interest in this group, but also because I find it fascinating. So the idea was to develop fragility curves. And you can do those fragility curves analytically. However, because in this project we had a lot of resources, they actually developed empirical fragility curves, or actually they calibrated these analytical models with shaking table tests of quarter models of the housing stock in the Netherlands. So here on the left, you have a quarter, is not a full house, it's a quarter model of a house in the Netherlands that was built on a shaking table in Italy. And in fact, in order to build this model, they even brought masons and material from the Netherlands so they can reproduce this housing stock as faithfully as possible. And with this, they develop fragility curves. So you have a host of fragility curves that show you probability of exceedance of some level of damage as a function of the input spectral acceleration. And these fragility curves are then convolved with the hazard curves. In fact, convolve is not the right word in this case. In this case, we use a Monte Carlo approach. So you simulate ground motions, and for each simulated ground motions, you simulate structural response using these fragility curves. And at the end, the result you have are predictions of risk. Okay. Any questions before I go to the results? Okay, you have to tell me, Kelly, if there's a question that's texted in because I cannot see the... Okay, the amplification factors. This is spectral acceleration at the surface over the borehole. We compute these essentially for every 100 meter by 100 meter pixel. Or it's called in 3 dimensions, it's called a voxel in this geostatistic model. So what we have is this prediction of side response all over the field. However, for purposes of predicting hazard and risk, we then group all these predictions into zones. And these zones are based on areas that have a common geology. And once you group them, we develop predictions of amplification function as a function of the intensity of the input motion, as shown here. Okay? And one thing that was very interesting and is an output that came out of this project is that these amplification functions for small magnitude are very strongly dependent on what's the magnitude and the distance. If you're interested in knowing why, talk to me, because I think this is theoretically very interesting, but it is a nice outcome. We have a paper that was published on this in 2017 that I think was one of the nicest academic outputs of this project. So at the end, for each one of these zones, we have these amplification factors, which means that we can predict amplification factors across the entire Groningen field. Okay, so here you have these predictions for 4 selected periods. These amplification functions are constant across each zone, okay, but of course vary across the field because they are different for each of the zones. Not only we predict the mean amplification, we predict also the uncertainty, because in the simulation of future motions, you have to account for this uncertainty. And this uncertainty has components that result from the variability that we see here, which results from the fact that the profiles change across the field. There's uncertainty in the shear wave velocity profiles. There is variability in the input motion. But this stage of the analysis was done using only one set of modulus reduction and damping curves. However, we know that we have to inflate our uncertainty because of the contribution of the uncertainty in nonlinear properties. This is the element of the work that was done by Maddie. So the idea is to do side response analysis where we look at the impact of modulus. What is the additional uncertainty that results from uncertainty in the nonlinear properties? And we develop, or I should say Maddie developed a nice model that allowed to predict these uncertainties across the full field. One thing that we don't have in this model is model error. And we postulate that our uncertainty cannot be lower than a certain value that is representative of the potential errors in our model. Our model is equivalent linear one-dimensional response analysis, assuming vertical propagation of shear waves. So we use existing data, existing work by John Stewart and James Kaklamanos to predict this amplification, this model error. And we are actually, this is work that Maddie is doing currently, updating this model with actual recurrence on the site. We also postulate that we have an upper bound to our uncertainty, that we really cannot have more variability than the NGA West motions, because those NGA motions are based on very different sites that have simply a common proxy. Okay, so we have this upper bound. Let me skip the scenario dependent and let me just go straight to the sample hazard results. This is truly just a sample because this is data that has been updated. So this is just a sample from 2018. And what's interesting is that you get what's called local personal risk, and this is risk that an individual has of injury, and the number of buildings that exceed this local personal risk. Okay, so for example, number of buildings that exceed the local personal risk of 10 to the minus 4. This is one every 10,000 years. No, it's as indicated here. And as you go up, let's say to a local personal risk of 1 in every 100,000 years, the total number of buildings is about 1,000 in the entire field. Okay. Bottom line, no buildings are exposed to mean local personal risk greater than 10 to the minus 4, which is the norm that were set. But since these results are preliminary, I don't want to stay too much on these results. All I want to say that the output of the whole study is this type of risk curves. And these risk curves can be used in two different ways. They can be used to monitor, to change output of future gas production to reduce seismicity, essentially dial down future production, reduce seismicity so that you reach a target LPR. Or they can be used to say, well, we identify locations where we have risk that exceeds our target, and then we'll go and improve that infrastructure, which is really the plan that NAM had altogether. Okay, you can also try to plan on volume, on the future volume of production basically. So conclusions, I presented a systematic hazard and risk study that was conducted for the Groningen gas field. This study allows for the prediction of local personal risk as a function of gas extraction. And the site response analysis, we show that we can do actually site-specific analysis on a large scale to successfully capture spatial variations in ground motion prediction. Okay, this is it. Thank you, and I will be very happy